We'll proceed in vector summation and integral calculus. Vector summation and integral calculus, the arena in which we are pursuing the discussion. Vector summation and integral calculus. Okay, so in that phase we have done n partitioning of calculation of the area. If I have an area generated by a function fx, then I can go for n time partitioning of the area fx dx, and then I can calculate the Taylor series. This is mind-blowing invention through us, and we would publish it. Then we can go for n time division of a volume that is generated by fxy dx dy. Fxy is a surface equation. If fx is the equation of a curve, then fxy is the equation of a surface, three dimension, where the independent variables are x and y in xy plane. In xy plane, independent variables are x and y. In x and y are independent variable, and they make independent surface. They make an independent surface as xy plane. And on top of xy plane, we have a surface, and equation is fxy, and then in fxy, if I consider it as integrand and differential at d of x and y, d of xy plane, it will give volume underneath it. Okay, if I calculate, so fxy d of xy or dx dy, and then equal to whatever surface we are thinking, if whatever volume we are thinking, if I divide volume into n different parts with the linearity, the first volume is the volume of a cuboid, the next volume is the volume of a triangularoid, next volume is a volume that meets the equation x to the x square, and so on. If I continue doing like that, then again I'll come to a Taylor series, and that Taylor series of three dimensions fxy. Fxy equal to fxy at x equal to 0, y equal to 0, plus 1 by 2, and in bracket dfxy by dx into x plus dfxy by dy into y, bracket close, into x into y, plus 1 by factor 1. Hope I'm sorry. The next is dfxy by dx. The first is fxy at x equal to 0, y equal to 0. Actually, I read something like that, the volume that we use to calculate the Taylor series. So first Taylor series is fxy fx small f, and in bracket x comma y bracket close, d of d, and then in bracket x xy bracket close, d of xy or dx dy, and then integration sign. Okay, equal whatever it comes that I'm telling. So probably it will lead to the Taylor series. Then it will be fxy at x equal to 0, y equal to 0, x into y, plus 1 by 2, and in bracket dfxy by dx into x plus dfxy by dy into y bracket close, xy, plus 1 by factorial of 3, 1 by factorial of 3, d2 fx by dx square into x square, plus d2 fxy by dx dy, x into y by x into y, by factorial of 2 into factorial of 2, plus d2 fxy by dy square at x equal to 0, y equal to 0 into y square, and then whole bracket into x into y. This is what we have seen. If someone does differentiation on both sides with x and y, the first will become fxy, that is a Taylor series. Fxy equal to fx into y at x0, x equal to 0, y equal to 0 into x into y. If I differentiate it with dx dy, it will become fx comma y at x equal to 0, y equal to 0, f0 comma 0, plus plus, and then x square y square x. If I do dual differentiation, then x square will become 2x and y will go away. More or less, it will become I'm sorry, dfxy by dx into x plus dfxy by dy into y. Okay, plus Then next will become 1 by factorial of 2 d2 fx y by dx square at x equal to 0, y equal to 0 into x square plus dfx d2 fx y by dx dy into x and y plus d2 fxy by dy square into y square. Every differentiation is at x equal to 0 y. This is the dividing things into n different parts and then solving it. Okay, what about if I go for more dimension than this? What can be more dimension? Like calculation of the weight if I have a function in terms of density. If I have a function in terms of density, then what about calculation of the weight? I believe it is understandable. If I say I have a surface equation, if I have a xy plane, on top of it there is a surface, and surface equation is in height from the xy plane, and that is also called fxy. What about if I have a cube, if I have a cuboid, and in the cuboid every location that is x comma y comma z, every location in the cuboid, x comma y comma z, and that x comma y comma z has different density. What I'm trying to say, at origin x comma y comma z equal to 0 comma 0 comma 0, there is some density in the material. I have a cuboid material. Cuboid material can be made up of anything. Maybe probably made up of alloy of iron, gold, silver, aluminium, nickel. So many things are there. I have made a solid cuboid. Now one corner I have taken at origin 0 comma 0 comma 0, and then there if I'm measuring the density, the alloy, it is something different. If I'm measuring at any x comma y comma z, it is different. If I'm measuring at any x1 comma y1 comma z1, then it is different. Everywhere density is different. Now can I denote this as a Taylor series fx y z, small f and in bracket x comma y comma z? What would be Taylor series for this? If I go with the integration of fx y z with dx y z, okay, f and in bracket x comma y comma z bracket close, and then d of in bracket x y z or dx dy dz. If I do integration of this and limit is from x y z from begin to x y z end. So if I do the integration means multiplying the density f x y z is a function of density only, where independent variables are the location x y z. If I take any x y z and I place a function over it, or if I pass x y z in a function, Python function or something, it will return the density at that point x y z. If I multiply density with with the width width, length, and height, then it will give the weight. But weight at different portion is different. To have the complete weight, I have to integrate fx, yz with dx, dy, dz, or multiply fx, yz with x into y into z. Over a limit region, it will give the net weight of the cubicle. Then if I proceed in the same way, please watch our previous to previous video. If I proceed in same way calculation of the Taylor series, then we will now this is on imagination. Now I cannot say that I have a volume and then I am taking a cuboid. Now this weight calculation is full of imagination only. If I go for the weight calculation where I have x, I have a triple dimension. If I go for the weight calculation, then I have x, I have y, and then I have z. I have Z. These are the independent components. These are the components. Okay, all three are independent. What is dependent is the density. At different x, y, z, density of the material is different. Okay, if I multiply at any point density with the very small region around it, it will give the weight of that region. If density is smooth, density is not varying, density is constant of a material that is a cuboid, where this is x-axis, this is y-axis, and this is y-axis, this is x-axis, and this is z-axis, then that cuboid I can multiply with the anything along x-axis, any measurement kind of alpha, and then beta and gamma distance for a cuboid that is made of a length alpha, width beta, and height gamma. Then its weight will be alpha into beta into gamma. That is the measurement multiplied by the constant density. But if density is not constant, it is a variable over function. Okay, then I can write the full weight is fx, y, z multiplied by d. D is differential for the integration. D, small d of x, y, z or dx, dy, dz. And then integration from lower limit to higher limit. Okay, that you will give the full weight, and full weight is equal to, if I see, then what is the weight that if that I receive when I multiply the density at the origin? If this is the coordinate system, this is x-axis, this is y-axis, and this is z-axis, then there is origin here. What is the density at this origin? If I calculate the density at this origin and multiply by a factor called x, x is a distance along x-axis, multiply by a factor along y-axis and y distance, and along z-axis, along z-axis, the z distance. If I multiply 3x into y into z with the density that is at f000, it will give the net weight of this cuboid, considering everywhere density is whatever we see at origin, 0 comma 0 comma 0. We see different density at different point of time, different coordinate x comma y comma z. We see different density. Whatever density we see at origin, 0 comma 0 comma 0, that density if I multiply with the x-axis, with the y-axis, with the z-axis, up, the distance along x-axis, I have taken a fixed distance. Someone can say I am taking alpha, beta, and gamma. Okay, for the clarity that we will see little more time after it. For clarity, I have taken x distance along x-axis and y distance along y-axis and z distance along z-axis. Now, in this manner, if I multiply x into y into z with the density that I see at the origin, that is f 0 comma 0 comma 0, 0 comma 0 comma 0 is a kind of a location, it is a coordinate, and if I apply function over it, it will give me the density. Density multiplied by x, y, and z. Okay, density at origin only. I am saying this is the weight of the cube. Why you are worrying? You are saying weight of the cube is fxyz, d of xyz or dx, dy, dz, where xyz goes from begin to end. This is what the weight of the cube is. But I am saying the weight of the cube is f at 0 comma 0 comma 0. What is the density at origin? Multiply it by x, y, z. You are taking limit as x equal to 0 to x, y equal to 0 to y, and z equal to 0 to z. Yeah, multiply with the x, y, z. You will get the full weight. Someone would say, why you are kidding? It is not possible because density is not constant over the cube. Then what we have to do? First we did. So this is similar to what we achieved if someone is watching in the first dimension. If I were trying to calculate the area of this fx, if this is the fx and this is x-axis and this is y-axis, what is area of this fx? That is fx dx. That is the area. Okay. But what I did, what is fx at x equal to 0? This is the height multiplied by 0 to x. This x, if I multiply this with the height, then it will give the area of a rectangle which spans in height till here. It will go like this, and then width like here. This is the area of a rectangle. But this area I added extra because I need this much only. But I added here. Now to compensate that, I will take I will draw a rectangle. I will draw a arc. I will draw a tangent at x equal to 0, and then I'll calculate the area of this triangle. This line, from here this line, and from here this line. It forms a triangle here. Subtract this. Someone will say this part is remaining. Then I take dual derivative. If I take first derivative, it will be slant line. If I take dual derivative, then I'll hold. deep now. And then I'll try to calculate the area. Then someone says something again is missing. Then I'll take triple derivative, then I'll go even deep now. And then I'll close. Then this I'll keep going, and finally I'll get the actual area. Actual area is fx dx equal to whatever we calculated right now. Rectangle minus triangle minus 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 like that. If I do differentiation on both sides, I'll get the Taylor's rate. That is the concept. So here also, in the density manner, when we are talking about the four dimension density manner, then what is the weight of the cube? Weight of the cube is fx, y, z, dx, dy, dz, and integration x is from begin to 0 to x, y is 0 to y, and z is 0 to z. That is equal to f000. What is the density at the origin multiplied by x, y, z? Okay, but that will be very coarse term. That will be weight of the cube, considering the density of the cube is same as what it is at origin. So, but that is not true. Density is varying every moment. Then I would say, do one thing. Take a single derivative of fxy at x equal to 0. It is like a slant line we took in calculation of a triangle. Or when we are drawing the volume, then this is what we try. Volume means you take the dz by dx. If I am trying to calculate volume, then I have two planes. If this is x-axis, this is y-axis, this is z-axis. I have, or rather if I show it, then this is x-axis, this is y-axis, and this is z-axis. This is z-axis. Okay, if this is the case, then this line and this line, if I make a vertical cut, that is called xz plane, and this line, if I make a vertical cut, that is called yz plane, xz plane, yz plane. Now, in that manner, if I have two planes, xz plane and yz plane, and then we are kind of trying to calculate the a triangular region. If I'm calculating, if I have a surface like this, triangular region, if I have a surface like this, and x equal to 0, y equal to 0, that will be the height. If I take a slant line, that is dz by dx, if this is zx plane, if I take dz by dx, it will be a slant line. Okay, if I take dz by dy, then it will be slant line in yz plane. Slant line in yz plane. Okay, that doesn't look like here. And if I take dz by dx, if I take dz by dx, then it will be slant line here. This is the rectangular volume that it is making. What is volume of this triangular region? The volume, what we saw is 1 by 2. If I take xz plane triangle, then area is 1 by 2 dfxy by dx, dfxy by dx into x square multiplied by the y, that will be the volume. If I take in yz plane, then 1 by 2 dfxy by dy into y square multiplied by x, that is the volume. If I add, then I get the triangular volume. Similar man, if I'm trying to calculate the weight for the triangular region, that we can imagine it, that is not we cannot draw it because it is four dimensional, then it will come as 1 by 2 dfxyz d of fxyz by dx into x square multiplied by y into z. Okay, plus multiplied, I'm sorry, multiplied by multiplied x square multiplied by y into z plus 1 by 2 dfxyz by dy into y square, that will be a triangular region, multiplied by x into z plus 1 by 2 dfxy d of d means differentiation, d of fxyz by dz multiplied by z square xy. Okay, this is how it is. This is the weight we will get. What will be the weight? What will be the weight of a triangular density region? What will be the weight of triangular density region? Mean where I have dfxyz by dx, dfxyz by dy, and dfxy by dz available. Okay, then I'll calculate dfxy by dz by dx at x equal to 0, y equal to 0, z equal to 0. dfx yz by dy at x equal to 0, y equal to 0, z equal to 0. dfxy df d of fxyz by dz at x equal to 0, y equal to 0, z equal to 0. In that manner, the weight of the triangular density region will be 1 by 2 dfxyz by dx into x square into x square, okay, into y into z. That will be the area region. I have to multiply that plus 1 by 2 dfxyz by dy into y square into xz plus 1 by 2 dfxyz by dz into z square multiplied by y into x. Okay, if I add all this, then what we get? 1 by 2 outside and in bracket dfxyz by dx into dfxy by dz dfxyz by dx into x plus dfxyz by dy into y plus dfxyz by dz into z in bracket close into xyz. Okay, means whatever we terminology, what we are seeing in the middle, dfxyz by dx, dfxyz by dy, dfxz by dz. One is be multiplied by x, one is multiplied by y, one is multiplied by z. Means whatever we were seeing in the single variable area calculation, that please watch our previous video. Area calculation, that was there, it was 1 by 2 dfxy by dx into x. Last x become xyz, that is the volume. First x become first dfx 1 by 2 become 1 by 2 dfx by dx, it became like dfxyz by dx into x plus dfx by dx in single variable, that become dfxyz by dx into x plus dfxz by dy into y plus dfxz by dz into z. More or less x becomes x plus y plus z. Wherever we see x, when we are calculating the area in the single variable, in the three variable, that x becomes x plus y plus z. In that manner, we can go for the higher order also. If I go for a higher order, then we have x plus y plus z whole square multiplied by x into y into z. That whole square I have to take out. How much it will be? First, I'll keep x plus y whole square, x plus y as one entity and z as one entity. It will become x plus y whole square plus z whole square plus 2 into x plus y into z. 2xy, I'm sorry, it will become 2xz, 2xz, 2zy. Okay, as a whole, and then as a hope, this is the x plus y, I'm sorry, it is x plus y in bracket plus z whole square, that will be x plus y whole square plus z square, that will be first square x plus y whole square plus z whole square plus 2 what we said. Now we'll break this also, x plus y whole square, x square plus y square plus 2xy. Okay, how much will it total it will become? It will be like x square plus y square plus z square plus 2xy plus 2xz plus 2yz. This is what we are saying. We can settle it down. Now x square, if I see the x square whole in a bracket and then outside waiting guy is x into y into z. If I settle it down x square, then it will become 1 by factorial of 3 d2 fxyz by dx square into x square. Okay, plus y square will become similarly 1 by factorial of 3 d2 fxyz by dy square into y square. Same thing z will become. As far as 2xy is concerned, 2 I'll take it out because I can divide it later also. X into y will become d2 fxy by dx dy because 2 are there, x and y are there. d2 fxyz by dx dy multiplied by x into y divided by factorial of 2, factorial of 2. Similarly, we can do outside x, y, z is waiting. Then I can mix it here. 1 by factorial of 3 d2 fxyz by dx square into x to the power 3y into z plus 1 by factorial of 3 d2 fxyz by dy square dy square into y to the power 3x into z plus, like that it will go. Then we can take for the third, fourth term, fifth term, fifth. So third, fourth, first, second, third. This is third term. Fourth term will become x plus y plus z to the power 3 multiplied by x, y, z. That I have to break and then proceed the way proceeded for the single dimension and dual dimension, dual variable. Now left side we have fx, yz into dx, dy, dz, and right side we have this many. If I differentiate both sides with the dx, dy, dz or d of x, y, z, first will become fx, yz. This is what we want. Fx, yz. So fx, yz equal to, first is fx, yz at x equal to 0, y equal to 0, z equal to 0. Into x into y into z. If I differentiate 3 times with x, y, z, then it will remain as fx, yz at x equal to 0, y equal to 0, z equal to 0. That's it. Plus next term is 1 by 2 dfxyz by dx into 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 x square yz plus 1 by 2 1 by 2 dfxyz by dy into y square into xz plus 1 by 2 dfxyz by dz into z square into xy. If I do this differentiation with x, y, and z, all three, then first is x square yz, y will go away, z will go away, x square will become 2x, 1 by 2, 1 by 2, 2 will go away. It will become dfxyz by dx into x plus dfxyz by dy into y plus dfxyz by dz into z. Okay, plus then we'll go for other term. If I go for a few things I can talk. First term is 1 by factorial of 3 d2 is d2 by dx square into x to the power 3 x to the power 3 y into z. If I differentiate with x, y, z, 3 will come out. If I differentiate with x, y, z, then 3 will come out. 1 by factorial of 3 will become 1 by factorial of 2. It will, and then yz will go away. It will become x square d2 fxyz by dx square into x square by factorial of 2, where differentiation is at x equal to 0, y equal to 0, z equal to 0, plus d2 fxyz by dy square into y square divided by factorial of 2 plus z square by divided by factorial of 2 plus, if I go beyond it, it will be d2 fxyz by dx dy, okay, and then we have dx dy, okay, and then we have terminology as x into y, and then outside x into y into z is ready. It will become x square y square z. That I have to differentiate with dx dy dz. X square will become 2x, y square will become 2y, and z will go away. Okay, 2 into 2 will come out. Anyway, in division we have factorial of 2, factorial of 2. So all will go away. It will remain as d2 fxyz by dx dy into x into y. Similarly, someone can proceed. We can say this is the Taylor series for the four dimensions. We have density and the volume. So someone can calculate. This is our proof. This is not available in any of the book. If people are do not want through volume way, then they can directly take the single variable Taylor series, where we are not calculating by the we are not calculating by calculation of area. Then still we can replace x with the x plus y plus z, x square and x plus y plus z whole square, something like that. What I'm trying to say, Mr. Taylor is saying that if I have any function fx, then function fx can be represented as function fx at x equal to a plus dfxy by dx at x equal to a into x minus a whole square plus d2 by dx square into x minus a whole square. Means where we have, I'm sorry, hope I'll repeat it again. Mr. Taylor is saying any function fx can be represented at a0 plus a1 x minus a plus a2 x minus a whole square plus a3 x minus a to the power 3, where a1, a0, a1, a2, a3 are constant coefficients. To find a0, a1, a2, a3, someone has to do one thing. Calculate fx at x equal to 0. Then everything will go away. A0 will remain. So A0 is fx at x equal to A. Do the single differentiation of fx and calculate its value at x equal to a. Then dfx, first differentiation is dfx at x equal to a. First a0 term will go away with single derivation. Second term a1 will remain, other will go away at x equal to a. Then it will become a1 equal to first differentiation of fx at x equal to a. If I do dual derivative, d2 fx by dx square at x equal to a0 and a1 will go away with the dual derivative. Second term will come as 2 into a2, nothing, and then will become 0 at x equal to a. Then a2 will be 1 by 2 d2 fxy by dx square. This way you can find what about the three dimension. For three dimension, we can replace wherever I see x with the x plus y plus z minus a. Take a as 0. Okay. Now, as per the Taylor series, fx equal to a0 plus a1 x plus a2 x square plus a3 x to the power 3, like so, because a I have taken 0. Okay, now what we are saying is, please watch our previous video. We can safely take x and x plus y plus z. Because if someone is watching our video when we proved it for multivariate, two variable case, x and y, there we proved that the triangular volume, that is the case number one is a0, case number two is a1. That the triangular volume is whatever the we calculated. It is similar to if I replace x with the x plus y. Here we replace x with the x plus y plus z. If I do so, x plus y plus z, then if I have fx, y, z, then what is the value at x equal to y equal to z? Then everything will go away because x plus y plus z. Now the Taylor series is what we are saying is fx, y, z equal to a0 plus a1 in bracket x plus y plus z. This is what we are saying. Plus a2 and in bracket x plus y plus z whole square plus a3 in bracket x plus y plus z to the power 3. If someone is taking pure Taylor series, then he can replace x with x minus a, y with y minus b, and z with z minus c. It is up to him. We have taken a, b, c as 0. If I take x, y, z as 0, 0, 0, then everything will go away. Only a0 will remain. So a0 is fx, y, z at x equal to 0, y equal to 0, z equal to 0. If I do first derivative, then a0 term will go away, a1 will remain. If I take first derivative is what is there in a1? A1 in bracket x plus y plus z, a1x plus a2y plus, I'm sorry, a1x plus a1y plus a1z, and then next term. If I do single derivation, then a0 term will go away, and then first term will be a1 if I do the derivative with x first. If I do the derivative with x by dfxyz by dx, x first, other thing will go away, only a1 will remain that was associated to x. So a1 will be dfxyz by dx. So I can replace a1x with dfxyz by dx into x. If I take derivative with the y, everything will go away. Other thing will remain, but at the end I have to set x equal to 0, y equal to 0, and z equal to 0. Here in a term of a1x plus a1y plus a1z, a1x and a1z will go away. If I do derivative with the y, then it will become a1, it will become a1. So a1 equal to derivative with the y, dfxyz by dy. If I take x equal to 0, y equal to 0, z equal to 0, other will go away. So a1 that is sticking with y is dfxyz by dy. If I go, then we will get same thing. If I settle down the third one is a2 and in bracket x plus y plus z to the whole square. That will come a2 and in bracket x square plus y square plus z square plus 2xy plus 2yz plus 2xz. Okay, that if I break, it will become a2x square plus a2y square plus a2z square plus 2a2x into y plus 2a2y into z plus 2a2x into z. And this side we have fxyz. If I do dual derivative with x d2 fxyz by dx square, first term, second term will go away with dual derivative. Here, everything will go away with dual derivative. Only x squared term will remain. That will become 2. So it will become 2a2. And then I set x equal to 0, y equal to 0, z equal to 0. Higher term will go away. 2a2 equal to d2 fxyz by dx squared. a2 equal to 1 by 2 or 1 by factorial of 2, because 2 times I took the derivative of x squared. First it is 2x and next it is 1. 2 into 1 factorial of 2. So a2 become 1 by factorial of 2 d2 fxz by dx square. I can replace it here. A2 x square will become d2 fxyz by dx square into 1 by factorial of 2 into x square. Similarly, y square will become like that, z square. If I settle it down 2x into y, we have 2 into a2x into y. If I take dual derivative first with the x and first with the y, then with the y, everything will go away up to the 3 term and next will remain. And then if I set x equal to 0, y equal to 0, z equal to other will also go away. What will remain here is 2 into a2 into xy. If I take dual derivative with x and y, 2 into a2 will remain. That's it. Then a2 will become 1 by 2, not factorial of 2, 1 by 2 d2 fxyz by dx dy. Now I can settle it down to a2. So that is d2 fxyz by dx dy 1 by 2, 1 by 2, 1 by 2 will go away. And then finally it becomes d2 fxyz by dx dy into x into y plus d2 fxyz into z by dy dz into y into z plus d2 fxyz by dx dz into x into z. Someone can settle next term in this manner: x plus y plus z to the power 3, and take 3 3 derivative and then take d3 fxyz by dx square dy or something like that, the way you see. This is the triple independent variable Taylor series. Now someone can calculate for the 4, 5, 6. Only thing is, instead of x, you take x plus y plus z plus alpha, then x plus y plus z plus alpha plus beta. The way you grow in it. This is the full-fledged Taylor series. The idea was to proceed on the concept of the kind of we are thinking about talking about exponential. What is the value of e? If I have y equal to a square, the way we were calculating the bank interest term. If I have a bank which I have deposited money in the bank, then bank give the annual interest rate with c. C is 5%. Every year you will get 5% interest. If you deposit $100, after 1 year it will become 100 plus $5, 5% interest given. But it is accrued, means it become a recurrent after every year. After end of 1 year, your principal amount will become $105. On top of it, 5% will be applied. Okay, this is called annual interest. Annual interest. But interest can be computed every 6 months also. Interest can be interest rate is annual, but the recurring, the every time the principal amount is getting added to interest, and then principal plus interest become a principal amount, and then it is proceeding further. This accumulation, the calculation of new principal amount after certain duration, that if it happens, it can happen annually, it can happen every 6 months, it can happen every day also, it can happen every moment also. But interest will be applied every year. What is the mystery of this? Okay, one is called continuous variation, one is called discrete variation, and in all the calculation we will see division into n part, and then summation and integral calculus. Then through this we will calculate value of e also. What is e? If I say y equal to a to the power x, it is understandable. A is a value, and a to the power x will be a graph, and that is y. What is y equal to e to the power x? What is e? E is not a term at all. A can be 1, 2, 3, 4, 5, 6, or A can be anything, but A is E. What is E? Generally, we use in natural log. Natural means log with the base of E. If I say y equal to a to the power x, then x equal to logarithmic of base A. Makes sense? Of y. Y equal to a to the power x, then x equal to logarithmic of y with base A. Understand? What is base E? That is also called natural log. What is E? Okay, Euler used to be a very delicate mathematician, and he said, if you set A as E, then if you differentiate e to the power x, it will become ex. If you integrate e to the power, it will remain as ex only. Amazing, mind blowing. So those things we will talk. And what are the intricacies and what are the Euler formula also in the compound interest? Very interesting. That we will talk. Concept was to start today itself, but it's too long. I think. Okay, these concepts are not available in the book, I'm 100% sure. Two ways to find the multivariable Taylor series. One way is the placing x equal to x plus y plus z, and another way is thinking about the density and volume and dividing into n different sections. One is constant density, then one is triangular varying density, single slope, then dual varying slope, and triple, and like that. Please do not mind supporting us. +91 is India country code 9483160610 is the telephone number. +91 is the India country code 9483160610 is the telephone number.